introduce the use of subroutines in assembly. Subroutines are great if we have code that will be executed multiple times. If we have a particular set of code, we don't want to take up our precious limited memory by writing out that code over and over again. As we've mentioned before, we only have a little over 8,000 entries in the memory for our program code, which seems like a lot, but that can get used up quite fast if you have a significant program. So the way subroutines work is very similar to the way functions or subroutines in any other programming language work. You have a small snippet of code, you call the subroutine, and then you go back and you continue executing more code. It's very similar to what you may have already seen in Matlab if you remember learning about that in a previous course. So what happens when they're called? The current program counter, that is the location we are currently executing in program memory, is stored onto a stack. We'll talk more about that in a moment. Then we branch to the label for the subroutine, so we change our program counter to wherever the subroutine's code is located, and then we execute the code in that subroutine until we reach a return statement. And once we reach that return statement, then we pull or pop the program counter value that we have previously put onto the stack back off, and then that allows us to change our program counter to that value and to return to where we were called from. And so we continue executing the code after the call statement until we reach some other part of the code. So similar to gotos, subroutines allow us to not just fall through from one line of code to the next, but the difference between subroutines and gotos is that gotos branch unconditionally. They have no way of getting back to where they were sent from, but with a subroutine there is memory about where the call statement was and how to get back there. So just to summarize the commands that are associated with this, there is a call statement, and that is followed by the label for a subroutine. That's what initializes going to the subroutine. The subroutine code is just like any other code that you would write. You can have arithmetic operations, port operations, bitwise operations, and then once you hit a return statement or an RETLW, which is the same as a return but actually puts a literal value in W, that will actually bring you back to where the call statement originated. And so a return just returns without any value in W. The RETLW will actually put a particular literal value into the W register when you come back. So this is very useful for error checking, or it allows you to basically send different signals about what happened inside of the subroutine. So if you were waiting for a combination of a couple values on a port and you wanted to see what the combination of those values were, you may send different values back in W depending upon what happened inside of the subroutine. So how does the stack work? I like to think of the stack as being very similar to a dish dispenser that you might see in a cafeteria line or at a buffet. And so if you think about the dishes, they're washed and they're put back into this plate dispenser, oftentimes one at a time or several at a time, and they're pushed down. There is a finite capacity inside of the plate dispenser, just like there's a finite capacity inside of the stack memory. In the case of our microcontroller that we're using in this class, there's only 8 entries in the stack. And so what that means is you can actually call a subroutine, and within that subroutine you can actually call another one, and within that you can actually call another one, and we'll see some examples of that later on. But if you do that for too many subroutines deep, you will actually end up having more than the capacity of the stack taken up, and that is what results in what is called a stack overflow. And so the way stacks work is they are last in, first out. So the last plate that's put onto the stack is the first plate that people pick up. So the last program counter entry that is put onto the stack, the last subroutine that is called, that program counter value is the first one to be popped off with a return. And so here's an example of a subroutine. We have this subroutine called LT_ON. Here is the subroutine code down here, just some pseudocode. You'll notice the label LT_ON. There's a return statement at the end of it. And then there may be different code that's written inside of here that actually turns on a light. And so in this case, we want to check when port B bit 3 is high, we want to turn on this light. So we're doing a bit test, and we're checking port B bit 3 to see if it is high. If it is high, then we are going to call LT on. Otherwise, we're going to skip over and go to this next line of code. After we finish executing LT on and we hit this return statement, the program counter will have previously been stored, and that will have the location of this line of code. The call LT on will be stored on the stack, and so then it will increment by 1, and we will go back to the line labeled RL for return location. So here is another example of writing a subroutine. Write a subroutine that will wait until a normally open, that is a switch that is logic 0 until it is pressed, switch connected to port B pin 6 is pushed. So we're going to go into the subroutine, and it's going to check and see if that particular button or particular switch is pushed. If it is not, we're just going to wait, and if it is, then we'll go right back and continue executing. So before you get into this subroutine, let's assume that you've already handled making things digital or analog and handled the input and output issue with your TRIS-B and your ANSL and your ANSL-H. So inside of this subroutine itself, what do we actually need? Well, we need a label. We need the test for the desired port input, that is making sure that port B pin 6 is pushed, and we need a return statement. So let's put those elements on the page. So here, we're just going to call this wait RB6. That's going to be the name of our subroutine. And so in order to execute this, we'll just say call wait RB6. And of course at the end, we need a return statement. That's what's going to get us back. So let's look at what we might put inside of this subroutine. We could say bit test F, skip if set, port B, bit 6. And then we can add a go-to statement to go to wait RB6. This is an interesting example because the label that is used for the subroutine that we got to by calling to get into the subroutine can also be used in a go-to statement. A label is just a label. You can use it with a go-to and with a call. So we're going to call wait RB6. It's going to come in here and do this bit test, and so long as this port B bit 6 is not set, it will go to wait RB6, and it'll continue to loop here, testing and going back. But once it does detect that port B bit 6 is set, it's going to skip over this next line of code and hit the return statement. Thus, at that point, it will pop the program counter off of the stack and return back to where it was called from. This is an example of what is known as data polling. So data polling is constantly waiting for a particular input, like what we had in that last subroutine. We were waiting for a particular pin to have a set value, and we just checked over and over and over again. We don't know how many times that loop would run, and if you're waiting on a human to push a button, that could be a lot of different checks before that happened. It might be a matter of seconds, it might be a matter of minutes. That particular button might not get pushed all day long. So what's the problem with polling? Well, while your processor is dedicated to waiting on that particular button to press, you can't do anything else. Your code is dedicated to that particular command, just waiting and waiting and waiting, saying, hey, is it pushed yet? Is it pushed yet? Is it pushed yet? It's almost like a child in the back seat of a car on a long road trip saying, Mommy, are we there yet? Are we there yet? Are we there yet? And so not only is that frustrating to the driver, but it also wastes his or her resources while they're trying to attend to this continual request. They can't concentrate on the road and perform their other functions as well, dedicating as many of their resources to the normal task of driving. The solution to data polling is interrupts. We have not yet talked about interrupts in this code, but that will come later on. Effectively, an interrupt is handling something in real time as soon as it happens, while being able to continue executing other code in the meantime while you wait. So more about this in a future lecture. We'll have a future lecture dedicated exclusively to interrupts. So here's another subroutine example. Write a subroutine to blink a light on and off 3 times? Well, in this example, we're actually going to have a few subroutines to make it more efficient. So in this case, we could introduce a subroutine called blink, and that blink subroutine could set port B bit 0, and then we could call another delay function. So this will be a delay subroutine that we have also written, and then we're going to clear port B bit 0 and then call for another delay. And so this will blink this particular port on and off exactly 1 time. So we'll set it, delay, clear it, delay, and then go back. Well, we wanted to do it 3 times, so what we could actually do is have another subroutine called blink 3, which could actually call blink 3 times in a row. Call blink, call blink, call blink. Well, that works okay so long as maybe we only want to call it 3 times, we only want to blink 3 times. But if we wanted to blink something, say 100 times or 1,000 times, you could see how we could quickly run out of code just by writing call blink, call blink, call blink. So even though calling blink does save us some writing, we might want to actually do a loop. And so in a future lecture that will be posted very soon, I will also introduce to you how to do various types of loops in assembly. So in summary, up to this point in the course, you've learned how to do 6 more PIC assembly commands. We've done bit tests and bit test F, skipping of set, bit test F, skipping of clear. We've talked about the goto command. We've learned about the call and 2 different types of returns. We've had regular return that puts nothing into the W register, and RETLW, which puts a specific value, a literal value, into the W register that you can use later. And you also, at this point, know how to write if statements and subroutines in assembly. Be on the lookout for a future lecture where we will talk about different types of loops that you can do in assembly.